What I'm going to talk about today is vocal markers of neuropsychiatric condition with a focus on autism and schizophrenia. But first, a slide on who I am. That's how I spend most of my days these days. When those two little ones who might pop up at a certain point leave me some time, then I work as an associate professor, as Daniel was saying, in cognitive science, and I have a background in communication, and I spent some time at the Santa Fe Institute and a few different places around the States. And my focus, I don't want to repeat too much, but is on coordinative efficacy and the other side of the medal, that is in which ways social interactions can actually fail, not as much in terms of, this person seems awkward, but actually how the impairment or awkwardness or conflict unfolds as we interact, trying to understand actually what is going on there. And that has also led me to study meta science. That is, how do we manage to do stuff together in science? And you'll see some sneak peeks of that perspective in my talk today, but also on emergence of language, where we're working on different ways in which people can develop novel communication systems, or in which ways we can make sense of 100,000-year-old engravings from South Africa and stuff like that. But how does this fit with vocal markers? Well, of course, vocal markers are part of the social impairment, and the approach of meta-analysis and replication feeds my interest in meta science. But really, it all started about 10 years ago, when I overheard from the neighboring office researchers saying, my IST participants do speak in an atypical way, but I cannot make it show on the spectrum. I can really hear it, and I cannot show any quantitative aspects. And I said, well, 3 months ago, I learned how to code in MATLAB, and I know some small stuff in machine learning. I'm going to show you. And 10 years later, I'm still trying to figure out how to do this properly. I should also mention that there's potential conflict of interest, in the sense that I consult on these topics for Rush and for the Children's Hospital of Philadelphia. But as I hope you see, there is not much reason for concern. So what am I going to talk about? The plan for the talk is trying to tackle why we should even care about vocal markers. I'm sure that you're already persuaded, but I think having a bit of meta perspective helps. Systematic review of evidence for vocal markers of autism and schizophrenia. Then our ongoing attempts at generalizing the existing findings on cross-linguistic corpora. And finally, a sneak peek of challenges and new direction that we just recently started taking, in particular looking at transfer learning and transdiagnostic approaches. Long list of collaborators. I'm not going to name all of them. And I should also mention that a lot of them are present in most of the work that I'm going to present. I'm going to give priority to students and show their pictures only in the specific studies. So why should we care about vocal markers of neuropsychiatric conditions? The first point is that from the very early descriptions of many of these conditions, such as autism and schizophrenia, a phenomenological description of a certain atypicality just pops up in the very early description. For instance, Asperger was talking about this pedantic tone that his children, that now we would say with autism, had. Kapperlein would talk about these difficulties in expressing emotion in the speech and voice of his patients. And indeed, these early nuggets of intuition made their way into many of the clinical scales that are used in this field. For instance, in the communication subscale of the ADOS tool for autism, or in the flat affect and alogia items of the negative symptom scales in schizophrenia, where the clinical practitioner is asked to give a Likert as a score from, let's say, 0 to 5 to how flat the voice sounds, for instance. So if we can actually create more objective acoustic descriptions of these phenomenological impressions, we might help scaffolding clinical practices. So we might help, for instance, with consistency in ratings across clinicians, which is quite a known problem in psychiatry, especially for early career clinicians. But we might also, perhaps more excitingly, enter into the domain of personalized psychiatry and medicine, because vocal markers are a potentially cheap, non-invasive, and dense measure, meaning that it can be used to more continuously monitor, if they work, symptoms, cognitive impairments, and the progression of those during treatment. Of course, when I say non-invasive and dense, this is from our researcher perspective. There's something that we should be more aware of and do more, that is actually investigating with the patients and the clinicians whether they are perceived as non-invasive and something that we want to have measured all the time. Further, as a researcher, I think that one of the holy grail of vocal markers for these conditions that in many cases are difficult to pinpoint in terms of mechanisms is that they might give us a window into mechanisms that are involved in the disorder. If we can describe from where these atypicalities come and how are they shared or not across disorders, we might get a better grasp. So since this is something that has a lot of potential and it has been talked about at least from the 20s, we should have a lot of evidence so far, right? So we went and did systematic reviews and meta-analysis, two of which I'm going to talk about, one on schizophrenia and one on autism. We picked some keywords. I'm not going to go through the details, but that enabled us to find several tens of traditional statistic articles looking at whether there is a difference between the diagnostic groups in a given acoustic feature, and much fewer machine learning articles trying to use a bigger set of features to automatically discriminate between the groups. And yeah, we looked at different kind of moderators. The only one for which there was enough data was task, which we'll come back later. That is, in which context was the speech recorded? Was a constrained task, like reading aloud a given text? Was free speech, like describe your day or describe the video that you just saw? Or was it a dialogue? First, we look at how cohesive is the field. So these are the papers from the two meta-analyses, and the links indicate citations between them. What we can see is that the field in itself doesn't seem too cohesive. Oops. But at least for autism, there is a cluster of citation where it's much more likely for a paper on autism, vocal markers of autism, to cite a paper on vocal markers of autism than a paper on vocal markers of schizophrenia. When we look at how much these papers refer to each other, we see that on average, a paper refers to about a third of the previously published papers on the same topic. When we look at schizophrenia, the situation is slightly worse. We get 4 different clusters plus a bunch of papers that do not cite nor are cited by anybody. And there is about a fourth of the possible citations that are used, right? But of course, one could say it doesn't really matter whether they cite each other. We can aggregate the evidence meta-analytically and provide the cohesion that the field has been missing so far. Not going to go into the details of the methods, but this is Bayesian meta-analysis with skeptical priors, which we ran with Jeremy and Stan. So when we look at group differences, are these diagnostic or are autists different from controls in the way they speak? We find that mostly pitch or fundamental frequency values, measures and duration measures, such as speech rate and the number and length of pauses, are measured. And we find reliable differences for pitch mode, that is how high people speak, and for pitch variability, that is how much they swing in their pitch, with autists showing higher pitch mode and higher variability, but also for pause number. Right? They have more pauses per unit of time. There is no effect of task, and there is a medium robustness to publication bias. Right? When we look at schizophrenia, more or less the same features are investigated, but the only reliable finding that we have is a humongous increase in pulse length for people with schizophrenia, with a Cohen's d of almost 2 standard deviations of difference. And there's some other trends like pitch variability or speech rate or proportion of spoken time. Even more interestingly, we find that the task that has been used to record these data has a huge effect. And the bigger the cognitive and social burden on the speaker, the bigger the effects that we see. But we shouldn't trust these too much because the studies show very low robustness to publication bias. That is, if we assume even a small publication bias with papers that are significant, that show significant difference being even just 50% more likely to be published than non-significant ones, then most of the results disappear. When we look at clinical features, right, meaning the symptoms of the disorders, we see that both in autism and schizophrenia, researchers have focused on total scores. That is, each of the symptoms, let's say flat affect, alogia, lack of motivation in engaging with others, get a Likert score from 0 to 5, and then they get summed up together so that you can get a patient with the same severity of symptoms who has high psychotic symptoms but low negative symptoms, such as depression-like symptoms, or a patient who has the opposite profile that score the same. And unsurprisingly, we don't get any connections between acoustic features and that. If we look at more specific features such as flat affect and alogia, which more specifically name voice and speech in their descriptions, we see that the meta-analysis only shows reliable results for the proportion of spoken times in the duration of the recording, where the less the patients speak, the higher the flat affect score. And again, tasks make these effects bigger. When we move to machine learning, what we see first is that the kind of features that are investigated explodes. So we have many more descriptors of speech, intensity, and duration, but also we start connecting to more contemporary speech signal processing literature with multiple measures of spectral and cepstral features. The proliferation of features, however, has also another side of the coin, which is suddenly the studies are not really overlapping in the features that they're exploring. So that if we take any two machine learning studies within one of these two diagnoses, on average, we will find less than 10% of the features recurring in the two studies, which make it, as you might imagine, very hard to see which of these features might actually be important in discriminating between the groups. When we look at the results of the machine learning algorithms, we see that predominantly in both fields, we have linear discriminant analysis and support vector machines. And that for ASD, most of the studies cross-validate their accuracy and report accuracy scores between 70 and 96%. But the exact number shouldn't be put too much focus on because sometimes these results are balanced, meaning they take into account the fact that the samples for the two diagnostic groups might be in different amounts. Sometimes they don't. So it's hard to evaluate exactly how much we should trust that accuracy. For schizophrenia, again, the situation is the same with a largely overlapping cross-validated accuracy between 75 and 87.5% in discriminating between the diagnostic group and the matched controls. So if we want to reflect a bit about what we learn from these meta-analyses, well, we can see that in terms of evidence accumulation, we have a fragmented field. People are not citing each other extensively. They're not relying on each other's results extensively. They're not paying too much attention to the features that, for instance, other machine learning studies have been using. We have that most of the studies have small sample size, slightly above 20 patients on average per study. We have, except for that humongous pulse length effect in schizophrenia, relatively weak univariate effects. Right? So we had, for instance, in autism, the biggest one was 0.48, which correspond, if it held on new data, to a discriminative accuracy of about 60%. Just by knowing, I think it was pitch variability, we would be able, if the results holds, to discriminate with a 60% accuracy. We also see that there's largely promising but not validated machine learning results. And by not validated, I mean that they're only present in that specific paper and they've not been tried out in different samples. We also see that there is a limited attention to clinically relevant use of the methods. We all claim that we would like to have our research have an impact on the clinic, but we see that in most cases, the problem that we give the algorithms is a clear-cut binomial problem. Patients who are very clearly, let's say, autistic and healthy controls that have no specific morbidity, no doubt that they're controls. Right? It's a starting point, but this is not very relevant for the clinical practitioners, as they tell me. What they want help with is the cases that they have a hard time discriminating, is the cases with many conditions that are competing with each other. There is little work on generalizability. There is no cross-diagnostic work. Actually, I think there is one paper that looks at depression and schizophrenia, but that's it. And there is little attention to assessment and monitoring of clinically relevant features. As I said, mostly they look at the total score across many symptoms, which is not very useful to the clinical practitioners. Or, to me as a researcher, when I try to understand what is generating these atypical patterns. Further, there is little to no theory development. That is, mostly these studies are motivated by, just like I did, by these phenomenological impressions of difference in the voice, but not from theories about how they might come to be. Mostly there is the general theoretical argument that if there is an atypicality in production, it must be because of atypical perception, right? Which has some ground, but it's kind of disappointing as the only mechanism suggested. So first, we want to keep up the good work that we started doing on these systematic reviews. And two of my students, Nicole and Luise, they put together a website called METAVOICE, which is freely available on METAVOICE.AU.DK, in which all these meta-analyses are being put up and where it's possible to keep easily updating the website, and the meta-analyses get automatically updated. And this is to sort of push an open way of doing research, even if it's just aggregated data. It gives me an interesting case for when I do meta science. It provides critical pedagogical experience for my students, but it also gives open data to plan future studies. And we have a bunch of developments that we're interested in implementing, some inspired by Daniel's very nice paper, for instance, overviews across diagnosis. We're going to steal your visualizations, Daniel. If you go there and you have a look and you have feedback and additions, so you want to submit your papers or your results to us, we'd be very happy. But this is how the literature looks. What I'm interested in knowing is, does it actually generalize, right? And why do we need to care about that? The first one is that when we see these studies, right, we have a high heterogeneity between studies, different ways of doing things, different effect sizes reported, but also small sample sizes, which are always a warning flag when we work with heterogeneous populations like psychiatric populations. Second, because we know from the replication crisis that many findings cannot be replicated when repeating the experiments, so a bit of skepticism should be warranted. But also, we have several papers now pointing out that even meta-analytic results tend to be 2 to 3 times bigger than the effects that are found by multi-lab replication. And we have some work with Maya Mathur now in preparation where we try to figure out why, but that's a different story. This is particularly crucial because if we want to promote a clinical use of these markers, this requires a more nuanced understanding of what generalizes, right? So within participants, do we see these patterns stable over time? if the condition is stable. Like, do we see these patterns generalizing across settings, recorded on a mobile phone at home or in the clinic with a professional mind? Which of these tasks should we use? Like, do they generalize across different things that we can ask the participant to do? Say, or actually having a conversation, will that give us the same information? We want to generalize between participants, right? We have potential new patients. We have diverse subpopulations inside these conditions, but also between populations. Let's say that I see some fantastic work coming out of your group in the States, and I want to see whether I can apply it to the Danish population. Well, we should know what can be reused and what should be retrained. If it doesn't even make sense to retrain using the same features. Plus, this might give us some theoretical feedback about what is specific to the condition and what is modulated by language, culture, task, and so on. So we set up some new corpora, cross-linguistic, with larger sample sizes than the literature and repeated measures. We, for reasons due to pandemics and other funding issues, we focused on monologues, in particular animated triangles or retelling a story. Basically, our participants see videos and have to tell us, after all, what has happened. And we were planning to collect a wide range from prolonged phonation to dialogue, but that didn't happen because of lockdowns and funding not being available. But we will do that. When we look at autism, we have a Danish and an American English corpus. When we look at schizophrenia, we have Danish, the Chinese, and the Japanese corpora that I'm going to present the results of. And we just received a German data set that we're currently pre-processing. So, do the statistical findings looking at a feature at a time replicate? And this is work that is part of Alberto Parola's Marie Curie postdoc that just started in my lab. These were the previous results. And when we look at whether they replicate in our corpora, what we see is that for autism, the only finding that we have across the American and the Danish data set is that pauses are longer. None of the three previous findings of pitch mode, pitch variability, and pause number replicates across both datasets. And when they do within one dataset, we find smaller effects. When we look at schizophrenia, we find that two of the trends, but not previously reliable findings, actually are found consistently and reliably across all the three datasets, in particular that pitch variability is lower and speech rate is slower. The humongous pause length finding, once we clean the data and control how things are measured, is not found in any of these three data sets. And the two findings that we can replicate, the two trends that we can replicate, are one half the size, pitch variability, and the other a fourth of the size for speech rate. When we look at clinical features, and now we can look at more things because we have more complete data sets, we can see that in autism, the only acoustic features that cross-linguistically and reliably relates to the different scores of the ADOS scale, and both the total ones and the subscore, is speech rate, with Spearman-Rose correlations of about 0.3 or less. Everything else is inconsistent across languages. When we look at schizophrenia, we get that speech rate and proportion of speech, given the duration of the recording, are, again, relatively weak cross-linguistic relations with both the total symptom scores in the negative symptom scale, but also with flat affect and alogia. Again, the size is about 0.3 or less using an experiment approach. So, hold up reflection, what we see is that there are three acoustic markers that can be found across languages. They all have small effect sizes, and they're not the reliable ones from the meta-analysis, which was a bit disappointing. which is not a vote of confidence for the generalizability of patterns, of acoustic patterns across voice, across languages, and for mechanistic explanations, easy mechanistic explanations. But what about more sophisticated prediction-oriented machine learning approach? Maybe we're just taking too simplistic an approach, looking at these features that were easy to extract in the 80s, and therefore we got stuck into them. So this is work that just got submitted as their thesis by 4 of my students, Emil, Marie, Stine, and Astrid, where what we did is to set up a machine learning pipeline that was as conservative as we could imagine in terms of, for instance, not having leakage of data across different partitions. I'm not going to go through the detail of that, but basically we take 20% of the data, which is held aside and never touched. That is not used for normalization or feature reduction or any of the steps, and it's very nicely balanced in terms of gender, age, socioeconomic status, and so on, so that we can keep a very nice validation set for our machine learning algorithms to be tested on. We had to choose some machine learning studies because we couldn't start with replicating all of them. And as we went through them, we got reminded of how heterogeneous they were. And also we found how underspecified their design choices are. And in particular, do not ask me of hyperparameter tuning, because we had endless Zoom meetings trying to figure out how the hyperparameter tuning was done in any given paper, or even how it should be done in order for the model to work appropriately. We chose studies in which the acoustic features could be extracted with OpenSmile plus minimal tweaks to ensure that these could be easily extended to new data sets. And we focus on traditional non-deep machine learning because of our limited sample sizes. In particular, we ended up sticking with studies that were using support vector machines with linear RDF and sigmoid kernels. Initially, we had thought of testing also the actually trained algorithm for these studies, but it was impossible to get hold of them or to get the weights in some way. And the studies that we chose to replicate were then Markey et al. 2015, Shaheen et al. 2019, and Chakraborty et al. 2018, which present some sort of cross-validated measures of performance. Recall for the autism between 78 and 86%, and F1 scores for Chakraborty at about 0.77. Right. So we fit the processes that they talk about in our pipeline. I'm happy to talk more about that in the questions if you want. And what we do is that the original recall for the ASD was between 0.78 and 0.86. In our case, on the holdout, we get between 0.56 and 0.80 according to which kernel we use and which language we're looking at. For schizophrenia, the original one was 77, and we get something between 0.6 and 0.7 according to, again, which kernel in which language we're looking at, which I think is a bit lower, but it's largely competitive. However, when we take the train model on one language and try it out on a different language, let's say we train following our old procedure on Danish, we get a nice recall, and then we try it on American English, we get chance level. And that's across the board between all these languages using all these algorithms. First, this means that we should maybe also test it on new same language data sets, which we haven't done yet, and we should also try cross-linguistic training, which we haven't done yet. But so what have we learned so far? The first, at a meta level, is that while trying to read through these papers, we found that the choice of which algorithms to use had some theory behind and something that we could sort of learn from. The choices between hyperparameter tuning are absolutely opaque and never reported. And even when we went through the literature and tried to figure out what would be the best way of doing that, that's really hard to do. It's really an artisanal practice, it felt to us. And that's maybe, hurting our ability to accumulate and replicate results, because we cannot do what the other people have done, and we cannot see the rationale for that. But also that training procedures do seem to generalize and give comparable results. But trained models do not seem to do so, at least if we take our cross-linguistic results at face value for now. More work to do. And we think that there is a value and a need for good pipelines and better documentation to more effectively explore the importance of specific features and cumulatively develop better approaches. Right? For instance, systematically benchmarking all algorithms and features on our own data before trying out new fancy approaches. And I know I'm preaching to the choir here. I've seen you have a few papers from the lab on pipelines for neuroimaging, but I think it's an important point, and it's something that has not been really available in this field. And generally, we need more critical collective exchanges. We need to work together. We need to compare our notes. So, challenging a new direction. So, where do we go from here? So, the first venue that we are trying to explore is transfer learning. So the idea is that we have a scarcity of high quality, large clinical data sets for obvious reasons. Like there are reasons, for instance, in Europe, of GDPR, privacy, concerns of the patients, and so on and so forth. And the trained model that so far we have tested seem to have a low generalizability. We cannot really reuse a model trained on Danish on American English. So what if we were to use more widely available and freely accessible data for pre-training? We know that many of the phenomenological descriptions of neuropsychiatric patients often involve emotional atypicalities. For instance, robot-like speech for autism, flat affect for schizophrenia. And after Googling a bit, we can find a lot of emotional speech that is available in many languages. For instance, curated actor-generated speech, but also somebody who has taken a lot of speech from YouTube and labeled the valence of the speech. So what we did is to take 3 of the most controlled data sets as a starting point, 2 produced on American English, 1 on German, in which actors pronounce the same sentences with a sad or a happy tone. And we use them to train on each data set 10-fold cross-validated random forest based on the MFCC's coefficient to predict the valence. And we do that separately by each data set. So we end up with 3 different algorithms trained on the 3 data sets. Right. We then create a mixture of experts, basically a system in which every time that a new data point is presented, the data point is compared to the training data sets, and each of the models is weighted according to how similar the new data point is to the training data set of that specific model. So each of the models produces a prediction, and that prediction is weighted by how similar the test data is to the training data set. And then what we do is we go a bit wild. We take a completely different context. This is 2 projects in collaboration with Rush, one on the left on Parkinson's disorder, led by Konstantinos Sekidis, and the one on the right on depression, led by Leslie Hansen. With Konstantinos, we took a corpus of Colombian Spanish speech produced by patients with Parkinson's disorder and match control. And we were interested in seeing whether our mixture of experts, without any retraining, would be able, just by labeling things as sad or happy, to provide information about the divide between Parkinson and controls. And the data that we had was phonations, E, and reading aloud sentences and dialogue. For the Danish study, lesser studies on depression, we had a Danish speech corpus with first episode depression patients and matched controls. And we were interested in reconstructing the presence of depression based on the autobiographical interviews that they gave to the clinical practitioners. And I would like to stress that not only the mixture of experts had never seen patients, who was only trained on these actors, but it also is applied to languages that it had never seen before. Albeit they're all Indo-Europeans, right? So Spanish and Danish belong to the same general language family as the training languages. What we see is that if we look at read sentences and read dialogues, actually just the scores of balance that the algorithm is producing give us effects of about 0.8, 0.9 standard deviations of separations, which would correspond to an accuracy of about 70% in discriminating Parkinson disorder patients from controls, and a correlation of about 0.4 with the severity of the speech impairment. When we look at depression, we see that, again, not having seen these data before, not having been retrained, the area under the curve that we can get just by using these happy, sad, continuous scores is about 0.77. And there's a comparison. Lasse, in his bachelor thesis, was using traditional features, as highlighted by a really nice systematic review by Cummins, training on part of these data set and then testing, and he was getting an area under the curve that was very comparable, 0.76, albeit the trade-off of false positive and false negative was 50. These is one of the directions we're going. The other is moving into transdiagnostic approaches, and this is led by one of my really amazing students, Ludwig Olsen. Where what we did is everybody's focusing on these monodiagnosis studies. What if we have several diagnostic groups at the same time? We have a corpus of Danish adults, autistic, depressed, schizophrenic, and matched controls. Again, doing the animated triangles because it's a very popular task in our clinical research areas. What Ludwig did is generated a bunch of 6-second voice clips, sliding of 1 second, and did lots and lots of noise and reverberation augmentation, because what he really was burning to try out was a deep learning approach, where the features could be learned from the spectrogram instead of us having to hand engineer them and define them from the literature. I should also mention that this was a proof of concept. We had set aside 30 participants as test, but as we were learning how to build these more complex models, we went a big back and forth after seeing the test results, so they're likely overfitting. So how do the results look like? If we do as in previous studies, right, we use the machines simply to discriminate between patient and control within one diagnostic group, we see almost perfect F1 scores. And again, take them with caution, they're likely overfitting, but they're pretty impressive results. If instead we take all the 3 diagnoses at once, plus the healthy controls, we see that the F1 score drops to a 0.62. We did some error analysis to understand what went on. And what we could see was that a large portion of participants with schizophrenia was getting misdiagnosed with depression, and that quite a few participants with ASD were also getting misdiagnosed as depressed. While it was relatively good at isolating the healthy controls, it had kind of a big bias for depression. I'd say misdiagnosed, but we all know how complex the field of psychiatry is. So actually there are, often comorbidities between these disorders, and many of the symptoms are actually overlapping between the diagnoses. Right? So the algorithm might actually be picking up on something. It just doesn't fit the black boxes of the diagnostic category. Which brings me to my very last point, which is some work that is at the very beginning and run by Line Kruse and Solveig Mathiasen, where we're starting to look at the individual clinical and cognitive differences, where we want to deconstruct the diagnostic block and actually look at specific clinical features, possibly across diagnoses. And here there are huge challenges that we're struggling with. So there's very little data available where we can actually have all these clinical scales and cognitive scales available. When we look at different clinical scales, within diagnosis, but even more between diagnoses, they're hard to compare. Their description of the symptoms are not fully overlapping. But also there is a lot of interdependence between cognitive and clinical features. And in the plot, there's some work by Lina and Solvay on how different symptoms of schizophrenia and cognitive abilities are related to each other. However, we have very vague dreams of interconnected algorithms that are separately trained on the specific symptoms, but they can transfer information across each other. And seeing how these algorithms trained on one diagnosis tell us about patients from a different diagnosis. But again, this is very vague at this stage. So wrapping up, what have we learned? Simple approaches do not seem to help much. Need more research on ability, transfer learning, and transdiagnostic approaches. And we are very far from clinical applicability. We are also very far from voice findings feeding back into our understanding of the condition. And, I'm just as culpable as everybody else in the field, because doing these studies, trying to just assess whether we can find differences and discriminating is much easier than going back and thinking about the model, theoretically driven model that should motivate these atypicalities. And here are just some ideas of what we want to do next. So we need larger open cross-linguistic data set, clinical and not. And I say open because there are good models from neuroimaging where we have a hybrid approach where you need to justify your need to access the data, and that preserves some of the privacy and ethical issues. We need easier to share pipelines and motivated algorithms. We need work on clinically relevant features, and over time, we need theory and generative models. And we also need to consult more with the patients and the practitioners to make sure from the very start of this research that we're not just producing algorithms that are not really helping and maybe are even perceived as invasive. With that, I thank you and sorry for going a bit over time.